Good morning to everyone. Today we are going to see about that op-amp application. In our analog integrated circuit, we'll be having that fundamental of operation amplifier, its functioning and performance. So today we are going to see the application of operational amplifier. The first one we are going to see one of the main application using a operation amplifier is a 555 timer. The 555 timer we may operate it in two different mode. One is astable mode, another one is monostable mode of operation. In this monostable mode of operation, we are going to use the 555 timer to measure the speed control of a measurement unit. In monostable operation mode, if the input trigger pulses are generated from the rotating wheels, the circuit will be determine the wheel speed. So whenever that drop the below that predetermined value, the monostable which will help to control the speed of a machine. How did you calculate the time period in a monostable operation of a 555 timer? That can be calculated with the help of a 1.1 RC. And how to maintain the 50% of cycle in a astable mode operated square wave generator. For example, in a square wave generator, we are going to use a two resistor. They are namely resistance R1 and R2. The first resistance which will be connected across a supply voltage and a discharge terminal, and the second resistance which will be connected across a discharge and the load terminal. So if it is the case of the value of the two resistance R1, R2, how will we obtain that 50% of duty cycle? What will be the value of the resistance R1, R2? So for example, in this case, the astable mode of operation square wave generator, the duty cycle can be calculated with the help of R2 divided by R1 plus R2. Here we have to maintain the resistance of R2 and R1 are the equal value. Then only we will get the 50% of the duty cycle operation. The next one is how to calculate a duty cycle in a astable multivibrator for a operating frequency of 150 Hz and the discharging time, it will be the 2.5 milliseconds. In this case, we have to calculate the duty cycle. We know the formula in a astable multivibrator. The duty cycle will be calculated in the way of total discharge time divided by total time period into 100. You will be getting a duty cycle ratio. Here they are given that discharging time of the given case is 2.5 milliseconds. They are given that its operating frequency is 150 Hz. We have to calculate the total time period. Total time period T, which is nothing but 1 by F. So you will be getting the value is 6.67 milliseconds. So by using the value of 6.67 milliseconds for the total time period, and also the discharging time is 2.5 millisecond, then you calculate your duty cycle, you will be getting nearly 37.5% of a duty cycle for a given astable multivibrator. The next case, at which instant the given device will be act as a free running multivibrator. At which instant we are going to call the given multivibrator as a free running multivibrator, which is nothing but is very simple, and we know that everyone, the voltage control oscillator, it will be call it as a free running multivibrator. What is the output voltage of a phase detector? Phase detector we are using here, one of the important parts in our voltage control oscillator. So in this case, that phase detector role is it has to find is error voltage will be present in your given system that can be detected with the help of a phase detector. And that the next one is at which instant the state of a phase lock loop tracks any changes in the input frequency. At which instant we have tracked the changes of phase frequency, that is phase lock state. In that state you will find the exactly input supply frequency which will be mixed with that output frequency. There should be a equal one. That is we are going to call it as phase lock state. And the next one is what is the function of a low pass filter used in our PLL. In this PLL, that low pass filter is used to remove the high frequency noises which will be present in your voltage control oscillator. And that the next and the last one, and in the PLL, how to maintain the lock-in range The lock-in range is nothing but the changes in the frequency of incoming signal can be tracked when the PLL is locked, so that the range of frequency over which PLL maintain in the lock with the incoming signal is called as lock-in range. Pullin time, which is depends on the Pullin time, which is depends on initial phase and frequency difference of two sign, overall loop gain, loop filter characteristics. These are the main factor to find the Pullin time of a PLL. Thank you for watching.